Good afternoon. My name is Neil Peterson, and be presenting today on dynamics and long-term development of the Appalachian forest from a tree ring perspective, from the perspective I have learned from the trees. And this is a part of the Global Climate Commons and the Appalachian Forest special session that Betsy has put together. I was supposed to be there a year ago. I really wish I could have been there. I miss being in Kentucky, but this is our world today, and I hope you and yours are as well as can be. And let's get into the talk. Um, okay, let me figure out how to advance the slide. Okay, there we go. And so I'm going to be showing you a good bit of data. I believe in data. I believe in showing data and telling stories with the data. And you know, I am the presenter today, but this is really the work of many, many people, some of whom are pictured in the center of this slide. Um, but they are from works that are in a book on dendroecology, a chapter that I wrote there, and then other works that we've had over the last, I don't know, 4, 5, 7 years now. It's been a while. But this is a summary, a distillation of some of these and many other things that me and my colleagues and my research teams have put together. And so one of our major concerns about forests and climate change is how will they change into the future? And it's a very hard thing. It's a very hard question to answer. We know that the climate is going to change. We know that it's going to get warmer. It might get wetter, it might get drier, it might get it will get more variable. There's a lot of questions around there, but it will get warmer. We know this. The models for the last 30 or 40 years, the climate models are our temperatures are tracking what the models had predicted over the last 30, 40, 50 years. So it's happening. We know that it's happening. But we still know how completely the vegetation is going to respond. And so one forecast, and this is by Matt Duvenik of the Harvard Forest. He was of the Harvard Forest. He was a postdoc at the Harvard Forest. And he's at the New England Musical School in Boston. Their modeling effort across New England suggested virtually no change in the next 100 years. And that very well could be right. An older piece of work that in ways has been overinterpreted in what it means is by Lewis Iverson and others. Lewis just retired from the US Forest Service. And they took these climate models and potential vegetation and the climate predictions for the future and potential vegetation, and they ran it into the future and suggested that we could have very high change, a lot of change, or low change, which would still be, though, fairly significant. And this made a huge impact. But the important thing is that the climate space for the type of climate that individual trees and species live in will change dramatically. Whether the forest changes or not is a whole other question. But we have a lot of forecasts out there, and that the suggestions on what's going to happen with climate change are big. They're all over the place, really. From in some parts virtually no change, in other parts of the world, large change, and we're still grappling with that. But we can go back in time and we can get some ideas of how the trees might respond to climate change, and that's what I'm going to try to present here. Before we get too much further, though, I want to say that the work that I do is based on tree rings, and we use tree rings to go back 300 or 400 years in time to try to understand the dynamics lives of trees and then the forest and how they develop over time. A lot of ecology, however, unfortunately, due to time constraints of a person's lifetime, money primarily, funding priorities and things like that, is that most of our research has been of shorter time periods and using data and different types of investigation. And theory puts forth the idea that it increases the likelihood of pseudo predictions. And that's the best way that I can think of that for me, it was hard to understand what exactly this meant, but I've been working on it. And what this actually means is that projections are seemingly good, robust at shorter, smaller scales. At the scales that we study things, we study a small patch of forest, we study a small patch of trees, we study seedlings for a few years, but they are likely to miss the longer temporal characteristics of the underlying drivers. So what really changes forests over long periods of time? That's what that's saying, is it's not well studied because it's difficult to study. We don't have the time, we don't live 500 years, and so on and so forth. And that's the theory and idea of why these predictions are seemingly so scattered of how vegetation will change with climate change. And so when I think about the Appalachian forest, the southern Appalachian forest, but also the Cumberland Plateau and that region of the South. You can tell I'm from up north, but I've lived down south off and on for about 10 years, I guess. And this is a picture of the Smoky Mountains. These forests are first, they're amazing and beautiful and deep in character, but they have a mixed severity disturbance. And what that means is many different things can kill trees and many different things can change the forest. And because of that, and because of their high biodiversity, the directions, the trajectory of the forest, the mortality or the impact of different disturbance rates will be highly complex. And so this leads to complex forest histories that then if we can understand the history and try to roll it forward in time, well, that will give you a large range of potential responses and a greater amount of uncertainty. And so, our understanding of how forests up here in the northeastern US work is pretty good. Not great, but pretty good. But that's also because it's a simpler forest and there's fewer trajectories in forest development. And when I moved from the Northeast down to the Southeast for my master's degree and I first went into the Smoky Mountains, I went, oh, all those ideas we have about how forests work are great for the northern New England forest, where there's 3 or 4 major species, maybe 7 or 8. But down here where you can have 10, 15 in one picture, it's not going to be the same. And so this is what's fascinating to me, and this is what I think about. And so what I do as my science is what you see here. This is Dr. David Orwig of the Harvard Forest. We take increment borers, we core trees, we get their ages, yes, but we also get their growth histories and their trajectories, and they can tell us a lot about how forests change. And initially, when Dave and I were master's degree students around the same time, a good while ago, we did this one forest at a time, like that Johnny Cash song, one part at a time. So we did it one forest at a time, and we would understand the 300 years in this one forest. And it'd be really cool because it is really cool, but it doesn't tell you the bigger picture of how things, like I was saying about that theory, smaller spaces or shorter time scales or a mix of both. We hadn't had studies from a tree ring perspective that looked over large spaces over long periods of time. And that's what we did. And basically, to boil it all down to one slide, these are, and I hope you can see the blue laser pointer here that'll help you see what I'm showing you. But on the y-axis is width in millimeters. On the x-axis is year, as in individual years between 1600 and 2000. And the gray lines are individual trees. The solid colored lines are the averages of different populations in the Southeast United States. The orange and turquoise are Blanton Forest, chestnut oak, and white oak. The red is white oak at Joyce Kilmer in North Carolina. The yellow is a collection of different oak species at Lily Cornet Woods, again in southeastern Kentucky. And the purple is hemlock from Savage Gulf. And so many different species, well, a handful of species, different growing environments, and what you see between 1700 and then that vertical dashed line in 1774 is that growth is on average low, between 0.5 millimeter and 1 millimeter per year between like 1700 and 1774. And when we see this, we interpret it as the trees are growing in the understory. And then suddenly, right around 1774 and soon afterwards, growth basically doubles on average and maintains that level for over 200 years. And so our interpretation of this is from southeastern Kentucky to western North Carolina to central Tennessee, across many different species, trees are growing really slow because they're in the understory and they're not getting light. And suddenly there was a mortality event that allowed them to move into the canopy in the late 1700s and then persist to the day that we cord these trees, sometimes in the late 1980s, sometimes in the 1990s, no later than the early 2000s. So our old growth forests in this part of the world, a lot of the trees, not all of them, and not all ecosystems, but of these we sampled, they were put in place, they were moved from the understory to the overstory in about 5-year period, all at once, ecologically, geologically, all at once, within a 5-year period. And that's surprising because that's not what we expect of these forests. And so when we dug down into the trees, we started finding this, and you'll see that there are 3 white arrows here. The picture on the left is tulip poplar. The picture in the center is chestnut oak. The tulip poplar is in Virginia. The chestnut oak is in Blanton Forest in southeastern Kentucky. And then this is from Darren Rubino, a colleague in Indiana. This is ash from Indiana. And what these are pointing at is this broken wood or funny colored wood. It's hard to see. With a trained eye, it's obvious. But this is an event that suggested that these trees were defoliated in 1774. This is the 1774 right here between this laser. It's a very tiny ring. The trees hardly grew at all in 1774. And so I went into the literature. I reached out to Kerry Mock, who's a climate historian. He goes into ship logs and diaries and things like that. And he reconstructs climate in areas and places where there are no meteorological records. And I reached out to him. I said, I think a frost happened. Where can I find a written record of this? And he told me to go look at the Moravian diaries. And so we did. And then when I reported back to him that I found mentions that 1774 was an incredible frost event in western North Carolina, Kerry got excited. He went to all his records and he found in these blue circles all over the southeastern United States that there was indeed at least frost or ice reported and temperatures below 0 degrees Celsius, below freezing, below 32 degrees Fahrenheit. Thomas Jefferson wrote about it. George Washington wrote about it. Farmers on the coast of South Carolina wrote about it. Farmers in almost southwest Georgia talked about trees dying during this period. Peach blossoms were destroyed. Farms were destroyed. There's a lot of written record about this. Kerry didn't know about it. I didn't know about it. The trees knew about it. And we used the trees to get to this evidence. First through their own language and then through our language. And so this is what people observed. On April 5th and 6th, 1828, watermelon in January, there was watermelon in January. Peaches and plums were in full blossom by early March. This is just a compendium of observations in the southeastern United States. And then in this 1849, sorry, I'm going to back up a quick second. This is a review of late frosts in the southern United States that have been reconstructed by Kerry Mock. And I want to show you how unusual 1774 was. So let me start that slide all over again. I'm sorry. In 1828, there was a very warm spring in the southeastern United States. April 5th and 6th was the freezing event. But up until that point, there was watermelon in the markets in January. The peach blossoms and plum blossoms were full by early March. And then the frost came in 1828 and just wiped out these blossoms. There's records of this. There was a late frost in 1849. These are killing frosts. 1849, between April 14th and 19th, frost killed off a lot of vegetation, a lot of crops around that time period. There was another one in 1818, between April 20th and April 24th, another killing frost. And then there's this one in 1774 that I saw on the tree rings that I reached out to Kerry about, and he told me about all the sources. And you'll see that this frost event is much later, at least almost 2 weeks than the latest one Carrie had found before, more than a month than another one in 1828. And in Georgia on May 4th and May 5th, it was reported that large trees were killed by this frost event. In Kentucky, this night, which killed almost everything that was green. And so it was really bleak. It really impacted. Um, they started praying to God to send food. They were sending people to Pennsylvania to maybe get grain. Panthers were stalking villages with this 1774 event because the rodents and the small animals, because there was no food in the forest because it was destroyed, they moved to the villages to get food from people, as rodents do, and the panthers followed them. That's the idea of how this happened. And so this impact, which I only showed you 3 species and I told you what people wrote about, we see this across multiple species in the southeastern United States. American chestnut, red spruce, hemlock, oaks, tulip poplar. Almost all the species that we've sampled show this, and this had an incredibly hard impact simultaneously. 2 days in the southern United States impacted forests and impacted the trajectory of these forests for centuries, just these 2 days. But it wasn't just the frost event. It was the climate that led up to that I think contributed to this. It's never one factor. We shouldn't think it's that simple, and especially in complex forests like this. And so we have the frost event in 1774, but what you see on this figure is on the y-axis, the Palmer Drought Severity Index. On the x-axis is year. And this is highly smooth, but basically above the flat line is blue, which means these are wet periods. These are smooth data, but these are wet periods, and red is dry periods. And so here's 1774, and leading up to this, we have 1, 2, 3 severe droughts in about the 20 years before that, and that weakens the trees. It weakens the trees, and it kills some trees, and then it weakens them a third time with that third drought, and then the frost comes, strips the trees of their leaves, because the leaves came out 2 weeks earlier so that year, killed the tender new leaves, and then just shook the forest for centuries. And that's what I think drove this huge event that killed probably between 10 to 20% of the forest. We don't know really for sure yet. That's a broad guess. It's probably closer to 10, could be 20. I don't really know. We don't really know yet. But these 2 events are important because I said they impacted the forest for centuries. And let me show you some more data that supports this. And by the way, this is the Blanton Forest in southeastern Kentucky. Go visit it when you can. Incredible. These are really big white oak and chestnut oaks that you see in this figure, and they date back to the 1660s. And I just gave away the punchline of this part of the talk. So around this time when I was teaching in Kentucky, I got together with Ryan McEwen here in the orange vest on the right. And we went to Southeastern to Lily Cornet Woods to reconstruct fire history from dead and down trees at Lily Cornet Woods. I'm repeating myself. And Rob Watts was running the chainsaw for us, and we collected these samples, and it was really fun and cool. At the same time, Ryan, pictured here with the chainsaw, said, hey, there's this old building from the direct descendant of Daniel Boone, just outside of Lexington, Kentucky, and Lower Hards Creek. Let's get some samples and we'll date those beams too. I'm like, yeah, that'll be fun. We can do that. We can use tree rings to say when the trees were cut down before they were made into beams to make the house that the descendants of Daniel Boone's family lived in. So we did all that. And then we looked at the age structure of the forests from the beams here and the forests from the fire history study in Lily Cornet Woods. And this is what you see right here, in addition to other tree ring collections we've made in the state of Kentucky since the 1980s. And so what you have here on the y-axis are the number of trees per decade that we think have a pith, or the center of the tree. So when this tree may have come up at half a meter above the ground, or 1 foot above the ground, or 3 feet above the ground, somewhere in that height, when they went from seedlings to saplings. And then this is by decades, and you'll see that there's a huge spike of recruitment starting around 1650, 1670, 1650, 1660, 1670, and 1680. And then of the lower Howard Creek samples, only one of the 15 timbers predated 1660. None of the fire samples from Lily Cut Cornet Woods predated 1670. And this is important because, especially from the lower Howard Creek samples, these trees were cut down in the sometime in the early 1800s, I believe. And so if they're really old trees, they could have earlier pith dates before 1660. You know, they could have pith dates that go back to the 1500s. But of the 15 timbers that we got, only one of them predated 1660. And so this is what I call the Kentucky Wall. So this is a period when there was a lot of recruitment of trees simultaneously, in an ecological sense, recruited across the state of Kentucky, mostly in eastern Kentucky, but not entirely. This also includes Mammoth Caves. There's some nice collections at Mammoth Caves. And so like that last story where a lot of trees went from the understory to the overstory in the Southern Appalachians in 1774, between 1774 and 1775 and 1780, we have a recruitment event a century before that, that I can only think is another mortality event at large scale, at least the size of Kentucky. And so when we first published this data, I'll be honest, I didn't fully believe it. I mean, I did, it was what the data says, but I'm like, oh, what if there's a bias in my data set? And so I learned about Florence Holly, and I could talk a lot about Florence Holly, but I want to first say, not surprisingly, we recognize her as the first woman dendrochronologist in the United States in the 1920s. Not surprisingly, she did not officially get her degree in dendrochronology because her supervisor was not a nice person to other people, let's put it that way. And he denied signing off on her dissertation. She went on to have a great career in archaeology. She was a great scientist, wrote 300 papers, really important. But she also made these collections in the southeastern United States. These are samples that she collected in the 1930s and late 1930s, early 1940s, oak from stave sawmills. So she could go there and she could look at individual samples and she'd say, that one looks old. I want that one. This one is not old. I don't want this one. So it's a highly biased collection of very old trees where she could see the rings before she put them in her backpack, essentially. Highly biased. She did this research now 50 to 60 years before we did our tree ring research in Kentucky. And so if she is getting the oldest possible trees in the late 1930s, early 1940s from old growth forests, from sawmills, they should predate 1660. That's the hypothesis. But what did we find? In this top figure, you'll see that the age structure looks virtually the same as the age structure of the forest across Kentucky that I showed you just a few slides ago. We only have 57 trees. That's all we had time to collect, but the spike in recruitment is 1650 and 1660. If she collected 4 or 5 decades before us, I would expect the way we think these forests operate is that the spike in her data would be back here in the early 1600s, and it's not. And so what this says to me is that there was a synchronous event of canopy disturbance sometime around 1650, 1660 is when I think it happened. Probably late 1650s to mid 1660s. We're still working on this, so we're still trying to narrow it down. But there was one event at the scale of Kentucky, and probably larger, that changed the forest for centuries. And my hypothesis is the only thing that operates at that scale is drought. It could be the catastrophic genocide of indigenous people. I cannot rule that out, that the loss of people from the landscape allowed for a surge of recruitment in the 1660s. That it's synchronous makes me wonder how that happened exactly, but also It seems late for what we understand about the demographics of indigenous people in that part of the world, but that's a huge question that we're not prepared to answer yet. We're still learning. We're still learning. But well, the other thing that we do know is that there were severe droughts in the 1630s. There were severe droughts right around 1650, I think, 16, I forget exactly when. And then there was another severe drought in the 1660s. And in a meta-analysis that I'll spare you the details, this figure here, basically above zero is wet, below zero is dry, and I've observed mortality events in the eastern United States over the last 100 years. That would be year zero. In the years leading up to these mortality events that are reported in the literature across the eastern United States for the last 100 years, we see that on average, not always, but on average, moisture is low. So what this means is basically our synthesis for the 20th century of these kinds of observations is when it doesn't rain much, trees are more likely to die. Rocket science. But it's synthesized here. It's not perfect, but this is what we think. So we also think that drought maybe likely played a role in the recruitment of these trees in the 1660s, but we can't say for sure. It's really complex. But anyways, and when we go farther back in time, we know that there are much more severe droughts in the past. And so this is the 16th century mega drought. It's centered around between 1564 and 1573, and it's covered most of the eastern United States, was strongly expressed down here in central Mexico too. But it was a severe event at continental scales. And I'm showing you this because we think we have found evidence that drought kills trees in a couple different places. And when we go farther back in time, we see a much severe drought. So we need to think of drought as a factor of how our forests change. And moving forward in time, this warming that we know is going to come is going to make things a little bit drier. And so when you get the natural dynamics of climate, and it becomes hotter, it'll make those droughts drier and make those droughts hotter. And we do know that hot droughts are more likely to kill trees than cool droughts. It's a small distinction, but this is something that we think. And so I'm going to skip this slide because this is really unimportant. I'm sorry. But what I've shown you is that abrupt synchronous growth can happen in forests. And we know this is triggered by extreme events, notably extreme late frost, which can happen more frequently, hypothetically, moving into the future as springs become earlier and earlier. We're still going to get frost. They could be late frost. They could damage tender shoots. We see that there's ecologically synchronous recruitment at large scales in these forests. I didn't show you, but the 1660s event is a very large event. It's not just Kentucky. It's not just Kentucky Wall. It's a much larger event than that. And when we see this abrupt synchronous recruitment of trees, and we see abrupt changes and synchronous growth patterns, and we see extreme events like late frost and drought associated with these events, we got to think that in the future we should expect them again. They haven't happened much in the 20th century. It's been very mild climate relative to the past. It's been warmer. It's been a little bit wetter until recently. And so these events, these extreme synchronous events can also be called black swan events. Like the pandemic that we're experiencing now, black swans are these events that shake a system. They're kind of extreme. They're not fully predictable. You don't know when they're going to happen, but they change the system for years, if not decades or centuries. We think we're finding these, even in these extremely complex southern Appalachian forests, we're finding these types of events, which really does suggest that they're a natural part of the system. But as humans change the climate and amplifies the dynamics of our climate, we can expect more of these in the future. I'm sorry I can't be there in person to talk more about this. I probably can't make the discussion, but thank you for your attention.